So, today's class we are going to have some. We are going to continue the previous class, and we are not. So yesterday it was orthogonality. Today it's completeness. So how can orthogonal or orthonormal set? Uh, what is the condition that it can be complete, or how we can construct in an how we can have a construction where we can make this set complete. So before you remember we had orthogonality and orthonormality. Orthonormality was a condition where like the conical delta ij is 0 if the basis, if they are same, then it's 1. If they are not same, it's equivalent to 0 basis. If you remember yesterday. Means if you want to write it like a condition, so either xy can be 0 or xy can be 1, depending upon whether x is not equivalent to y or x is equivalent to y. Or this can be represented as delta ij. This is the but for an orthonormal set to be complete, so we say an orthonormal set is complete. Orthonormal set is complete if it's not contained in the log, if it is not contained in the larger orthonormal set. Yeah, no element of it, or it cannot be considered as a part of that set. So it's an independent, its own set. As we say, orthonormal set is complete if it's not contained in the larger orthonormal set. It's self-complete in itself. Now, having this understanding, we are going to have how we define completeness. So completeness as a condition can be defined as chi is a vector space having elements x1, x2, so on and so forth, is any finite orthonormal set in a product space and if any vector and if x is any vector and alpha I is xi, then there's an inequality called the Bessel inequality. Says I alpha I square is less than or equivalent to x square. So alpha square scalar is less than the inner product of these xi and xi. If xi it's xj, if I is not equivalent to j, it's 0. If xi is equal to xj, so it's the modulus is x square. So any scalar, the product of scalars is always less than this thing. So then the vector x prime is x minus sigma I alpha I xi is orthogonal to each other to each xj consequently spanned by this. So if this is a finite orthonormal set in a product space, that's fine. And if X is a vector such that this, then Besson equality says this. Then the vector this is an orthogonal to each xj consequently spanning by. So the vector xj is so how we can, so this is the general assertion. So the, or it's a sort of let it be, it's a theorem. So the assertion or the theorem. So these statements, how we can justify it in the context of the previous definition that an orthonormal set is complete in itself, and it's not composed of it from any other orthonormal set. You cannot get it from, extract it from any other orthonormal set. So if that is the case, so the completeness is defined that way. So if it is that way, so then this thing then it should be orthogonal to xg, consequently spanned by. So there should be an orthogonality condition for this to hold. So the assertion can be say, so for example, 0 is less than or equivalent to modulus of x prime square, or it's equivalent to x prime, so it's equivalent to x minus alpha I xi, and x minus, now you have alpha j x. So you can have two two spanning two these elements. One is xi minus alpha I xi, and other is xi minus alpha j xt. So if it's that way, then you can see xx. So you can have it like. So you can have it x this, you can have four terms: I alpha I xi x, then it will be xi xg alpha g xi xg. So we have so it's a complex conjugate because if you remember when we defined yesterday orthonormal sets. So one of the thing was conjugate, you can do it. And the fourth one is sigma I, sigma g, alpha g, xi, xg. So if you see it, if it's the product of, so it can be as a modulus of this square. So it's also alpha I square. And this is also, you can take it as if it's xi xg, if it's orthogonality condition I is equal to j, so it's 1. So it's the modulus of this equal to alpha I square plus ig alpha I square. So if you just see it here, this will cancel with this. So you can see that it will be xi square minus sigma I alpha I square. This is xi xg also could be one of them. If their orthonormality condition is there, so it will be alpha j square or alpha I square, I is equal to j. So this is the thing. So we have the first assertion is this. First assertion is this. First assertion is this. And the second assertion can also be similarly. You can have it if it's in the same way x prime xg or xi xg 1 sigma alpha I j xi xg is alpha g minus alpha g is this thing. So this is theorem 1. Now the theorem 2 says so the theorem theorem 2. The theorem 2 says that if this is a finite dimensional vector space, is a finite orthonormal set in an inner product space. The way we define product space, here one is complex conjugate. So how we construct a product space? Yesterday we have just done this and said the following 6 conditions must hold. So previously there were 2 assertions. So there are following 6 conditions or assertions must hold. So we have to say that chi are these assertions of chi in this space, a finite orthonormal set. These assertions are, assertion number 1 is the orthonormal set chi is complete. This is first assertion. The second assertion is if xi xxi is 0 for I is equivalent 1 to n, then x is 0. The third assertion is the subspace spanned by I is the whole space. The fourth assertion is if x is in V, then xxi x. And the fifth assertion is, sorry, it's a product of this. Fifth assertion is if x and y are in V, which is also called in literature as Parseval's identity. Then x of y is xxi xi yg. And sixth one. So if x is in V, then modulus of x square is xxi square. So the logic of this may be shown that we follow the book, or if we have a general argumentation, this follows this, this follows this, this follows this, this follows this, and from 6 we can arrive at the first one. So this is the way, the procedurally we are going to just see it that way. So 1 goes to 2 goes to 3, 3 follows 4 follows 5 follows 6, and 6 follows 1. In a sense, it's also complete, that it completes the proof also. You can start, you can begin and you can start, and you can reach, come back where you started. That's it. For example, 1 goes to 2. How can you explain it? 1 goes to 2. Orthonormal set chi implies. That's fine if I is equal to 1. x1 is 0, xi x1 is 0 or n is equal to 0. So one of them is perpendicular, so that way it's orthogonal, and that way it should show that it's 0. So this is fine. So first xi is 0 for all I for x not equal to 0. Then we may adjoin x by modulus of x to x. So we may adjoin this to x to obtain a larger orthonormal set. So in a sense, orthonormal set is complete in itself. But if you want to construct a larger orthonormal set from a given orthonormal set, so we may adjoin it with this thing to obtain larger orthonormal set. And from second to third, if there is an x, and which is not a linear combination of xi, then the second theorem, second part of the theorem is x prime is equal to x minus this. This is one theorem, and it's the adjoint thing which we have to it. Is different from 0 and is orthogonal to each xi. So if we construct it this way, it should be different from, so that means it's an orthogonal to it. So it's a sort of different from this, and it should not be that the case that. So the original thing is right, that subspace is the subspace spanned by chi is the whole space of that vector space, or of that orthonormal set. So anything additional to it, it's the orthogonality condition holds, and that will come out to be 0. This is 2 to 3, and now 3 to 4 is if x has the form alpha j xj, then x xi, we can have this scalar outside, so we can also have x xj xi. So we have defined xj here, so we can write it like this, and here is xj, so it will be alpha, it will be xij, it will be alpha I, because this jj is common, it's alpha, it will be alpha I. So this is the third, this is third to fourth. Now we can go to fourth to fifth. If x is equivalent to alpha I xi, y is beta j xj, then alpha I is x xi, beta j is y xj, then xy is alpha I xi, beta j xj. this means we can put the scalars both sides. We can get it in the prefix. So it's xi inner product of xi and xg. Again, if it's orthonormality condition, then xi xg product inner product of this xi xg it will be 0 and xi will be 1. So it will be alpha I beta G. So, but if you want to have I's beta G's, we'll have complex conjugate of it. So for 5 equivalent to 6 5 should be equivalent to 6, we'll put x is equivalent to y. Now we'll come to 6 should come to back to 1. So we restart it. It should come here. So if chi is is contained in larger orthonormal set, so it will lead to contradiction. Larger orthogonal set. Say if x naught is orthogonal to each xi, then I xi square modulus of this, it will be 0 orthogonality. So x naught is equal to 0. So this is the condition, first condition. So this is a sort of exercise that if there is a finite orthonormal set with an inner product, what are the different properties which can be associated with it? And can we do some things like if we want to show that the orthonormal set is complete, so if we want to, we add the orthonormal set with some adjoint, so the orthogonality should make that additional thing 0, which makes the original condition. We come back to the original condition. So now there is another thing which is seen. Something called Shiva's inequality. So this inequality has many interesting applications, not only as an analytical function, as a geometrical or mathematical. It has good geometrical, analytical, or mathematical properties throughout mathematics literature. So here we are studying them in relation to these orthonormality and orthogonality conditions. To begin with, so if we have a theorem, the theorem says that if x and y are vectors, in an inner product space, then she was inequality says x of y is less than or equal to modulus of x, modulus of y. Modulus of x, modulus. So this is she was inequality. So this is it. So what's the proof of this thing? How we can show it? And that. So if y is equal to 0, both of them will vanish. This is one thing. So if y is not equal to 0, then the set consists of maybe one of the elements. We can have this, which is orthonormal. So if it's not 0, that's fine. So that's fine. So if it's not 0, then One of the elements can be this. So the inequality can take this form x of y. If you just have this modulus of y square is less than or equivalent to modulus of x square. So now the arithmetic, geometric and analytical consequences, even though they are in different points. So but the thing is that in any inner products, in any inner product space, how do we define a distance? We define distance delta x y between two points, between two vectors. It's like similar. Sum of two sides of the triangle are always greater than the third side. In a sense. So in the same way, if the any inner product space, then two vectors x and y are defined as it's defined as x minus y into x minus y. Sorry. So in order that delta should have some analogy with distance, or if we want to appreciate delta in terms of distance, what are the properties which it should hold for the function? One is the symmetric property delta of xy should be equal to delta of yx. So the order of the elements should not change the relationship between the two. This is one thing. The second property is that delta of xy is greater than or equal to 0. This means delta of xy is 0 if and only if x is equal to y. The third property is delta of xy is less than or equivalent to delta of xz. The second property is you can have it because only at the origin x is equivalent to y. Only at the origin point x is equivalent to y is equivalent to 0. So this property you can see it from that. So the third property delta xy xz plus delta zy. So in vector space, it's also pleasant to be sure the distance is invariant under translations. Vector space. Under translations, distances remains invariant. So you can have a sort of confirm okay translations. And delta of x, y, delta of x plus z, y plus z. Now, here to prove the third this property, we observe that x plus y square modulus of these elements can be written as x plus y, x plus y. So now you can write it as individually. You can have x square, y square, xy, yx. You can have modulus of x square, mod x of y, x y, it's yx, so we can have complex conjugation of it. It can be written as y x of y but conjugate. It's y of square. Or it will be modes of x square. So xy conjugate, so it will be twice xy. Twice real part of xy. The other elements will cancel. So we can have this thing less than or equivalent to. Here you have shifted. So this step makes it whether it's equivalent to or less. It can always be less than. It's not necessarily that the other parts may cancel. Or x, y square. Or you can write it a plus b whole square. Modulus of x plus modulus of y whole square. Now if we replace x with x minus z and y with y minus z, so it will be x minus z and y with y minus z. So it will be, sorry, not z minus y, sorry, it's z minus y. So what will it will be x minus z and z will cancel. It will be, you can write it like this: x minus y is less than or equivalent to x minus z plus z minus y. So this is equivalent to third. This is equivalent to this. This is equivalent to third. This statement. One of the two. The real part of it's yes, we said it's the real part of this thing. And in Euclidean space, Rn, we can have xy modulus of x modulus of y gives us the cosine of angle between the two. And yes, this we did yesterday also. Now yesterday we did not we defined it that a space was defined as a unitary space, and in the product is one of the elements was the product was between element. In the complex space, the other element was the conjugate of that thing. So the way we define unitary space, the Schwarz inequality becomes the unitary space can be written as. So if we construct two sequences, the way we constructed two scalars previously associated with two vector spaces. So if you have two sequences, zeta 1, zeta n, and neta 1, neta n of complex numbers, then sigma 1 is equal to 1 to n, zeta I, neta I square is n is equal to 1 to n neta I square. So we can define it like this: zeta square. So in a sequence of two, so we can individually write it like this. So this is third. The fourth is, this is second. This was the one first. these are the properties. This is second property, this is third property, and the fourth property is, so if you define that space in some finite dimensional space in some sort of an integrand, the integrand is between 0 and 1. So x, y, x of t is 1. The another is the conjugate of it. This is this dt square. You can, it's always less than or equivalent to xt square dt, and 0 to 1 yt square dt. So this is another way of writing Chivas inequality. So there is also something called normed vector spaces. In those normed vector spaces, we normally assign those vector spaces not with angles but only with the magnitudes only. So we defined normed vector spaces in that sense, which has an acceptable length but will not necessarily be with length. And a normed space can be a complex vector space which has a numerical valued function. So you have this is like this. Now I'll write a theorem, maybe that what is the condition for a complete orthonormal sets. So there's a particular, might have heard, who had some link of it. So if the orthonormal set is said to be complete. So if you have an adjoint, how can you, if you want to add some adjoint of it, the point is how to construct a complete orthonormal sets. So if there is something missing, you can finitely reconstruct term by term till it becomes orthonormal. So if the orthonormality as a condition is not given, how we can construct orthonormality? Or the other way is that how we can show whether a set is orthonormal or not. These are the two ways stating it. And it's also in literature called Gram-Schmidt orthonormalization process. How we can construct orthonormalization as a condition, how it can be achieved, or how it can be shown that orthonormality as a condition exists or not. So there is a theorem which says, we are going to write it. If V is an n-dimensional inner product space, then there exists complete orthonormal set, complete orthonormal sets in V, and every complete orthonormal set in V contains exactly n elements. The orthonormality dimension of V, orthogonal dimension of is same as that of linear dimension. So if V is an n-dimensional inner product space, that's fine. There exists complete orthonormal sets in, that's fine. And every complete orthonormal set in V contains exactly an element. So it should be self-contained in that sense. So if it's not complete, we should have a way of or method of enlarging the set, term by term, enlarging the set to make it orthonormal, to make it orthonormal. That's the point. So it's a sort of maybe constructive method and a sort of crude induction is involved. How we can take procedurally from step by step the process. So there is another way of, so I'll just will only state it, and this thing is in the literature called Graham-Schmidt orthogonalization procedure. Yeah, yes, that's it. So, so maybe this is a good point to stop here and finish class. Stop.